Welcome. This is the Regression Analysis course. My name is Nicoleta Serbat. I'm an associate professor in the School of Industrial and System Engineering. The topic of this lesson is basics of multiple linear regression. Particularly, I will introduce the model structure of the data in multiple linear regression, along with variations from the standard multiple regression, including models with interaction and an understanding about different roles that variables take. This slide is a representation of how we describe any statistical model, specifying the definition of the data structure, the representation of the relationship captured, and the model assumptions, all embodying the data generating process. In multiple linear regression, the data are the response variable given the values of the predicting variables. More specifically, you observe end realizations of the response variable along with the corresponding predicting variables. The relationship captured is the linear relationship between the response variable and the predicting variables. The assumptions describe the probability distribution of the data. For multiple linear regression, we assume that the deviances, or the epsilons, denote as also called error terms, and defined by the difference between the response variable and the linear function in the axis, have zero mean, constant variance, and they are independent. For estimation, we only need these assumptions. However, for statistical inference, we also need to assume that the deviances are normally distributed. What does the mean assumption mean? It means that the expected value of the errors is zero across all errors, meaning also that the linearity assumption holds. Constant variance assumption means that it cannot be true that the model is more accurate for some parts of the population and less accurate for other parts. A violation of this assumption means that the estimates are not as sufficient as they could be in estimating the true parameters. It also results in poorly calibrated prediction intervals. The assumption of independence means that the deviances, or in fact the response variables, are independently drawn from the data generating process. Violation of this assumption can lead to misleading assessments of the strength of the regression. The assumption that the errors are normally distributed is needed if we want to do any confidence or prediction intervals or perform hypothesis tests, which we usually do. If this assumption is violated, hypothesis tests and confidence and prediction intervals can be very misleading. Another important consideration in statistical modeling is identifying the model parameters that are to be estimated using the observed data. In the linear regression model, the parameters defining the regression line, the betas, beta 0, beta 1 to beta p, are parameters, but we also have an additional parameter, the variance of the deviances, denoted with sigma squared. I'll highlight that model parameters are unknown, regardless of how much data we observe. We will never know these parameters exactly, but we can derive some approximations or estimates given the data. The parameters will take different values if one uses different data sets. In multiple linear regression, the model can be written in matrix format, in a matrix form. We define the design matrix as a matrix consisting of columns of predicting variables, including the column of ones corresponding to the intercept. The number of columns of X, or the design matrix, correspond to the number of predicting variables plus one, corresponding to the intercept. We also stack up all the values of the response variable into one column matrix, the same as for the parameters, the betas, and the error terms. The matrix formulation of the model is, as on the slide, y equal to x, the design matrix, times beta, the vector of coefficients, plus the vector of errors, epsilon. Let's take a closer look to the very simple model where we have two predicting variables. The model gives the equation of a two-dimensional plane or surface plus some disturbances due to the error. It states that for a fixed value of either predicting variable, the expected value of x is a linear function of the other variable. If we graph a regression function as a function of only one variable, say x1, for several different values of x2, we obtain as contours of the regression function a collection of lines. In general, it is often desirable for some predicting variables to be mathematical functions of others, in the sense that the resulting model may be much more successful in explaining variation in the response variable than any model without such predictors. The point here is that the linear model, when extended beyond many variables, is extremely flexible. The linear in linear regression refers to fitting the response as a linear function of the observed data, but it doesn't mean necessarily that the linear is a linear relationship in the individual predictors. In fact, we can extend this model to a second-order model where we include also the square root of the predictor. So we include an x1 square and x2 square as additional predictors. For this model, when we fix x2, the expected change in y for 1 unit increase in x1 is not beta 1, but beta 1 plus beta 3 x1. If we graph a regression function as a function of only one variable, say x1 for several different values of x2, we obtain as contours of the regression function a collection of curves rather than lines. Thus, while the estimation of the model is the same as that for a linear model, the interpretation is not. The contours of the regression function for model 3, or the first-order interaction model, are non-parallel straight lines. For any interaction model, they would be non-parallel. For model 3, the expected change in y when x1 is increased by 1 is beta 1 plus beta 3 times x2, thus depending on x2. This applies also to the fourth model, where we include both second-order and interaction terms. And this, it will be the contour plot for the fourth model. In a different lecture, we contrasted the simple linear regression model with the ANOVA model. In a simple linear regression, we consider modeling variation in the response with respect to a qualitative variable, where in the ANOVA, we consider modeling variations, the response, with respect to one or more qualitative variables. Multiple regression is a generalization of both models. When we have both quantitative and qualitative variables in a multiple regression model, we need to understand how to interpret the model and how to model qualitative variables. Assume a model with both quantitative and qualitative variables where the quantitative variable has 3 levels, thus decomposed into 3 dummy variables. We learned in a different lesson that when we have qualitative variables in a regression model with k labels, we only include k-1 dummy variables if the model has an intercept. Thus, for this example, we include the two dummy variables d1 and d2, not d3. The way the presence of the dummy variables as predictive variables impact the model is in that the intercept will vary depending on the label on the label of the response variable. So, for example, for those 3 models, if we have d1 equal to 0, d2 equal to 0, that means we consider the response variable for the third category. The model is beta 0 plus beta 1 x1. The intercept is beta 0. Now, if d1 is equal to 1, all the other 2 are 0, the intercept is going to be beta 0 plus beta 2. If d2 is equal to 1, then the intercept is beta 0 plus beta 3. So what we obtain are parallel regression lines. As we discussed in the previous slide, if we include the interaction term between the quantitative variable and the quantitative variables, the regression lines are non-parallel as shown in this figure. Let's go back to the first example where we're interested in the relationship between the sales and advertisement expenditure. In this example, we differentiate between quantitative predictive variables, for example, the total amount of bonuses, the market share, the largest competitors, and the qualitative variable, which is the indicator of the region in which an office is located. In the second example, in the third example, we're interested in differentiating between qualitative variables and quantitative variables that impact movie rating. And we have 4 quantitative predicting variables: number of votes, duration of the movie, total budget in millions, and several qualitative predicting variables. I want to highlight particularly the release year as a qualitative variable. Year can be also a quantitative variable, and we decide whether year is a quantitative or qualitative predictive variable depending on how many years we observe. If there are only a few years across many observations, in this case we have 5 years, different years of data, then we can consider it to be a qualitative variable. If the observations are made over many years, then we can consider a quantitative variable. Generally, we can transform a qualitative variable into a qualitative variable, into a categorical variable, particularly when we see that there are nonlinear relationships of that predictive variable with respect to the response. In this lesson, I presented the model structure of multiple linear regression, and we also overviewed the flexibility of this model in terms of providing more complex relationship between predictive variables and responses, including second-order interaction or other nonlinear relationships with respect to the response variable. We also discussed the difference between qualitative and quantitative variables. Thank you.